Thanks, Dan, for that quick introduction. Good morning, folks, and welcome to this webinar by Semiviki and Mirabus Design on architecture exploration of processors and system on chip using trade-offs between power and performance. I'm your host, Deepak Shankar, and I'm the founder of Mirabus Design, and I have worked for many years in supporting customers developing products, almost 250 products to date, in enabling architecture exploration and getting their benefits by using it efficiently. Before we get started, let's talk a little bit about where architecture exploration fits in the design process. And today we're focusing on IPs and SoCs. Most designs will have a variety of requirements coming from marketing, from the field, from proposals by government or other institutions, any combination of those. What we do is we take those requirements and select a series of IPs. The IPs can be selected based on business decisions, based on data sheets, any of those considerations. Once we do that, architecture exploration kicks in, where we take the data from the requirements, convert those into traffic, use cases, application tasks, those, and then take IP models that are available and construct up a block diagram. Once we have the block diagram, this becomes the architecture model of the specification. Now, these block diagrams have a lot of buzzwords associated with it, like transaction level, timing approximate, timing accurate, cycle accurate. But in a sense, it's a model that allows you to emulate two things. One is the components you're going to be using, and the second is the requirements details. Now, once we have this block diagram, we run a variety of simulations by varying the workload, varying the attributes of these IP models, and we get a variety of statistics and reports. Using those, we conduct trade-offs to determine, if I change the use case or I change a user type, what is going to be my response time, or how much throughput am I getting for the 20 sensors that are connected to this SoC. Once I do all of those trade-offs, I finally get an architecture that's been highly optimized for this target application, which is where I get an optimized architecture, plus I get a documentation that can be shared with the entire team, both internal, external. And I also get enough information to start off with my validation as well. So validation can be of three kinds. It can be where I get my early software and I'm trying to put this into the model to see what the performance timing attributes will be. The other one is to test specific IP, typically IP that has been built in-house, test those using a hardware prototype like an emulator or an FPGA board, and do field debugging. So once the chip is ready and you put it into a device and you want to test it out, you want to have a reference platform against which you want to test it. This is a nutshell what architecture exploration is all about. It's really concept validation for your entire system. So your system can be a single IP block like a network on chip. It can be a full processor, or eventually it can be an IoT device or a high performance computer. Now, before we get started, I just want to go over some key terms. As we saw, architecture exploration is really the exploration and analysis to come up with a specification that meets the requirement. System modeling, which is the umbrella under which architecture exploration comes under, is the ability to construct virtual models that have timing, power, throughput, functionality, without having to worry about generating the implementation code. So no schematic diagrams, no software seed code or Python code or RTL code in Verilog or VHDL. It's a model that does not require any of those in details. The information is there in the model of what is going to be constructed in those languages, but you don't actually have to have those languages or the data available in those languages ready to run this architecture model or the system model. Using the system model, we can run a variety of trade-offs. Trade-offs can be functional analysis, hardware, software prototyping, or partitioning, figuring out how many cores that need to be there. Do we have this completely distributed? So you have like multiple network on chips or network on chips with an AXI bus or a tile link bus. So you do these kind of trade-offs to come up with what's my optimized architecture. To be able to do these trade-offs, there are really three aspects to it. First is functional. Functional is where you're looking at the quality of your arbitration algorithms, your logic, your scheduling, things like those. Performance analysis is really all about the timing, which is buffer occupancy, the end-to-end latency for, say, a memory access, or the throughput that you're going to get from an ingress to an egress queue, those kind of items. Power measurement is the last aspect, and it's always left to the end, but it should really be done upfront in the architecture exploration, which is looking at what are the key components that are consuming power. Is there a way to reduce the power by doing some optimization? And also, what is my peak loading? I've got to, those things become very important when I start designing my power system as well, to figure out, how to maximize the efficiency of my system, at the same time, reducing the overall power consumption. The power consumption decisions that you make over here carry throughout your design process, because it impacts your customers, impacts the cost of your chip, impacts the mechanical devices, impacts your cooling. All of those get impacted by the design effort that you do upfront. Now, if you look in the past, most times you either used Excel spreadsheet or you used a whiteboard and you started drawing up these different options to come up with what you felt would be the best architecture based on prior experience or data from a prior project. Those things are now made more quantitative and qualitative. So what we do in today's architecture exploration is split the architecture into three segments. Communication, which is all about the buses, the interface, the NOCs, things like those. Compute and storage, which is anything from the CPU core, the AI, the GPUs, the FPGAs, the memories, the caches. And the last one, which is new in many cases, but it's all about the scheduling, it's about the network, it's about the arbitrations, the round robins, the fixed priorities, things such as those. Now, architecture exploration is about taking all of these, putting them into a model, and then running use cases and workloads on those. So to give you an idea of what those would be, I could have an architecture 1, which gives me, an architecture of this kind, which is, like every component has its own scheduling, or I can have another architecture where they're all using a common network or an AI setup for messaging. Now, how do you decide which one's right for you? It really depends on your application. One application may have architecture 1, another application may have architecture 2, or there's probably another 100 different variations. Being able to run all these explorations is really what architecture analysis and architecture studies is all about. Now, just to make it very clear, there are other tools that provide some aspects of performance validation or early software development. It also claims architecture exploration, but really architecture exploration is not early software development. It is not expected to do code generation or behavior synthesis, and definitely not usable for mathematical evaluation of the algorithms. Meaning, I'm looking at the FFT and I'm looking at the quantizers and I'm looking at the number of taps. That's not the job of architecture exploration. Architecture exploration is how much time is it going to take if I have this many coefficients and this many taps for my FFT? It's going to take on an FPGA versus a processor versus, say, a vector processing unit. Now, there are aspects of this that architecture exploration models can support, but this is not the primary role. Before we get started, I want to go over a quick introduction to VisualSim Architect, the software we're going to be using to describe this process of architecture exploration. VisualSim is a graphical and hierarchical modeling environment which has a large library of parameterized components. Now, these components are what users utilize to very quickly assemble a system. So, for example, you can put in together a off-the-shelf component SoC or a processor in a matter of 2 to 3 weeks. And you can put in a very detailed with all your custom logic, your custom arbitrations, your custom IPs in a matter of a month or so. And of course, after that, it's a question of doing analysis and exploration. One of the key things in VisualSim Architect is the ability to bring in mechanical, analog, electrical, and electronics and software into the same model because of an integrated simulator that has both discrete and continuous time. Discrete is where you look at the time at a position, which we call as synchronous activities or synchronous events between asynchronous time, or continuous simulator, which actually goes at every point in time. So essentially every single cycle in the design. So you can actually use both of those seamlessly within a single model. The other aspect of VisualSim is the ability for you to reuse either models that have existed within the company or models that you have received from third-party vendors through a variety of APIs that are provided. And lastly, the optimizer. There's an optimizer and a diagnostic platform that will predict what are the problems you're going to have in these designs, whether this design is applicable for the particular target application. So it's really a comprehensive architecture exploration environment. Now, I'm not going to take too much time on this because you can go to our website at www.wearablesdesign.com and you can see more details about all of these components. But as you can see, there are over 500 IP blocks available in this technology that you can utilize to very quickly assemble up your system models. Now, we talked about a little bit, which is compute and storage, communication, and arbitration. Now, each one of these has a variety of IPs that go within that. And when you collect all of these sections, it's possible for you to put a processor or SoC for a variety of applications. So you can look at something like an x86 processor, to a Drive PX from NVIDIA, to a custom AI accelerator for an automotive application or robotic application. Of course, there are also other very specialized processors that you can construct for like space applications or supercomputers as well. Now, let's first look at what are the analysis or evaluations that you typically do during architecture exploration and using these architecture models. Now, if you take a person that's building a pipeline for a next generation processor, there are a variety of analysis that you want to do at each stage of the pipeline. And as you can see, there are a variety of statistics that are generated for each stage of the pipeline. And these are what are used to make your decisions. One of the key things about the VisualSim reports is that it's sufficient for you to make the decisions and not a stage where you just are overwhelmed by the reports. The other aspect is the intelligent diagnostic tool that's available as part of VisualSim allows you to very quickly be able to figure out where the problem is. The diagnostics will tell you that your queue occupancy on your four-way decode is exceeding the limit, and as a result, you're having a flow control that's pushing back on the previous stages of pipeline. So you know exactly where your problem is. Where do I need to spend more time and focus? Similarly, when you're looking at communication, you would have a very different set of workload and analysis. So for example, here you can see, this is for a network on chip, where you can see I can set up different types of flit frequencies and network configuration and routing. And based on that, get a different amount of throughput. And which throughput is the best really depends on what my particular use case and my requirements are. Because if you put too high of a throughput, cost goes up. If it's too little, you're going to lose data. So you need an optimal architecture that will allow you to define exactly what your configuration is going to require, and also tell you exactly what is needed for your particular application at the right cost to meet all the requirements, and of course, looking at weight, size, cooling, and all of those other attributes. Now, let's go over those different processing components we talked about: communication, compute, storage, scheduling, arbitration. So if you look at a compute platform, this is the VisualSim library components for building up the pipeline of an ARM A77 processor. Each one of these is a block in the library. Similarly, when you look at storage, you can look, there's a separate ID, L2, a TLB, and instruction feed, and then of course the memory controller and DRAM. So these again form part of the cache and memory hierarchy library. Now, in this case, we got a 2-stage, but we also have models to go through 4 stages of the pipeline as well. On the communication side, you can get an AXI bus, you can get a PCIe, you can get Ethernet, you can get time-sensitive networking, CAN buses, and a variety of other devices. In this case, we're just looking at one aspect, which is a network on chip, which is, in this case, we're looking at the CMM600, but you can also get an Arteris NOC, or even something that's a fully customizable NOC, like an AMD Xfinity, or your own in-house NOC that you've constructed. Now, if you look at these, you can see that they all have the standard, like 4 connections to cross points to communicate with the other nodes, but at the same time allows you to have 2 or more devices connected to each of these XPs or cross points. Now, a third aspect, which is typically missed out by most system modeling analysis tools, is really the arbitration and scheduling. So today, in most CNNs or in AI systems, or configurable neural networks, what you have is a series of queues and a central memory with some sort of a logic or arbitration that will trigger off the execution of the different tasks onto the AI processing network. So some of it can go into the individual cores, some of it can go into an accelerator, and even some can go into DSP blocks or into GPU blocks as well. This network will allow you to enable that process. So this ability to create custom network management or arbitration is a unique capability of VisualSim Architect, which you will not find with either open source or other kinds of tools that are trying to go into the architecture exploration, but are really more on the early software development or performance validation, which is a term that is used for testing out your implementation after you've done your coding, and completely different from architecture exploration, which is done up front. Now, when you get these models and you try to run these models, you get a variety of outputs. So for example, here we can look at buffer occupancy, latency for 2 different configurations. Here you have the IQ buffer, clock speed and memory speed, and here you have a different one. And you're trying to compare the results between the 2. Matter of fact, if you notice here, between these 2, there's a slight difference as you get over here between the front end and back end performance of my particular A77 pipeline when I integrate it with the NOC and the memory and the caches and all the other subsystems. Now, we're going to do a case study to really understand how the methodology and how architecture exploration process works. We're going to take a system that's got a multi-core Cortex A53 running at 1.2 gigahertz with L1, L2, and external memory. We're going to use a multimedia application, and we're going to generate a trace for it. We're also going to use additional applications that we don't know about, but we're going to generate traces for it based on a stochastic process that takes into consideration the types of instructions, the type of profile that we can generate for that target application, which will be developed in the future. The hardware accelerator is something that is also available in the event that you might need to move some of these application tasks over to that. So when we look at the VisualSim model, what you see here is an ARM subsystem. You got an accelerator, you got the system bus with the DRAM and flash. Now, if you notice a few things, one is you got the architecture and then you got the software architecture. This is your application that is running on top of this target. Now, if you notice, there are two different scenarios. One here is the call network, which is making the phone call using the voice system. And here is the ability for you to look at the different scenarios of your multimedia. So what are we looking at here? We have the IP or ARM level where we're looking at the pipeline stages, the clock speeds, the amount of memory, the cache sizes, things like that. At the SoC, you're looking at the number of ARM cores, the accelerators, and of course, the cache memory hierarchy at that stage. Now, at the system level, this would eventually go into a product, say an IoT device or an engine electronic control unit, or even into an integrated platform that might become like, say, a space application for avionics or a supercomputer. So this here is what you're looking at is the VisualSim model of an architecture. You run the first case where in this scenario, what we're trying to do is we are trying to run this with all tasks being run on the A53 core. And you can see that the number of frames per second is going to be about 23,000 at the peak right over here. Now, the power is almost 1.7 watts of power, which does not meet our requirements, which is the performance has to be significantly greater than 23,000. The power is okay because it has to be less than 2 watts, so we actually meet that. Now, notice the hardware engine has not been enabled, but you can also see statistics on some of the other blocks within the system. So you can see, for example, on the system bus, how much entered, exited, and what was the buffering. You can get that kind of information as well. Now, based on the analysis, we see the sensors and the application triggers. Based on this, we see what the timing diagram is, the sequence diagram is for this whole system. And we find that the rotate frame is the one that consumes the most amount of time, which means that's the one that is consuming the most amount of resources. So what we do is we try to move this particular element over to a hardware accelerator. So the next stage is where we're trying to get to the target performance, which is the over 100,000 frames per second. But now we see the power is gone from like about 1.6 to almost 2.3, 2.4. And we also notice those are my hardware engine that is running, spiking up every time there's a requirement, and then it's going down to some sort of a standby state. You can see now how the data has modified here with a hit ratio of 98%. And you can also see, there's very little prefetch, because it looks like most of it is running within the cache as well. But you can also see what the activity is on the cache subsystem. Now, what we want to do is we're happy with this number. We're happy with the performance, but now we're not happy with the power. Case one, we're happy with the power, but not with the performance. So what we're going to do next is we're going to do a power management on the same system. So we're going to be found here, as we saw earlier, that the hardware accelerator is only active for a short period of time. So which means that we have an opportunity to reduce the power for the hardware accelerator when it's not being utilized. So what do? We now try to run the same thing, but we turn on power management, which is for the period of time that the hardware accelerator is not busy. As you can see over here, we allow it to spike up, let it go for a certain period of time to ensure that nothing is going to come during the time. And then we drop it down to a complete idle state. So with this process, we can get the power considerably down. And as you can see, we got this below the 2 watts of power. So that way, we have managed to achieve our power goals. And notice at that time, we have not really reduced the performance. So the number of frames per second hasn't been impacted right over here. So this way, we can achieve, by running this architecture exploration, achieve the architecture or the system that we can get for our particular requirement. So with this, I'd like to thank you for attending this webinar on architecture exploration of processors and SoCs to trade off power and performance. And I'm your host, Deepak Shankar. If you have any questions, feel free to send me an email at this address.